what's going on in the velocity versus time graph, okay? And how do we connect those back and forth? Because people have a lot of trouble with that conceptually, so I want you to focus on how this relates to what you're doing in the lab, okay? So we're going to start with what we're going over in this chapter. So we'll start by basically throwing out a lot of definitions. We'll talk about displacement, time, average velocity, then we'll talk about instantaneous velocity, talk about average and instantaneous acceleration. We'll talk about some special cases like motion with constant acceleration. Then we'll talk about a special case of constant acceleration, which is free fall. Okay, so G. And then we'll talk about integrals. So, don't freak out. Okay. So, just some goals for this chapter. We're going to want to describe straight line motion. So we're going to use all these definitions to just talk about what happens in the real world, but in physics words, okay? Then we're going to do graphical interpretation. So you're going to learn to look at a graph and figure out how to know what that means in terms of actual movement of actual objects in actual life, okay? Then we'll talk about how to solve problems of 1D motion, so free fall, and then more general cases, okay? Free fall is a special situation, but it does come up a lot. If you go to a baseball game, you've seen free fall, okay? If you fall out of a plane, you've experienced free fall, okay? So, just to start out with, in case you were wondering, physics and math, not different, okay? Why was calculus invented? Physics. And so who are the two main guys that get credit for like calculus? Newton and Leibniz, right? And so what's the difference? There's different notations. And there's Newtonian, right? So this is, if you have a function, how do you take the derivative? Which is much easier to write than Leibniz notation, because one of the things, we don't know what we're taking a derivative with respect to. It doesn't give you a lot of information. So if you have df, and let's say we want to take a dt, time derivative. So this, you'd have to add this back in. This is the first derivative. This is a time derivative. This is a much better notation, okay? Because we're going to do some questionable things with this notation that your math professors would be like, no, don't do that. Technically, that's not true. But it works really well in physics, and we'll go through it, okay? You can actually treat these as, so like df, that's like a tiny derivative of f. And when you get to multivariable calculus, if f is a function of x and y, then you can actually use it to take derivatives of x and y, and it's much more general. But the coolest thing you can do with this is, let's say you have df dt is equal to 3, and you want to figure out what f is, okay? You can df is equal to 3 dt, integrate both sides, okay? Which is why Leibniz notation is far superior to Newtonian notation. And so this is where patriotism can get you into trouble. The British physicists used Newton's notation because he was British for like 100 years. And they got really behind in the math and physics from the rest of the continent that were using Leibniz notation, because this is just a better way to write things. Like, there's no mathematician you can talk to that's like, no, Newton notation is better, okay? Unless they're just like, they don't want to write more stuff. Okay, the only advantage is it's quicker, but this is a much more robust way to write a derivative, and you can do a lot more with it. Okay, so that's the biggest side. But physics is calculus. Calculus was made to do physics. They have never been a separate thing. Okay, so we're gonna get into this, but remember, this class, it requires calculus, but I'm going to walk you through it, because the way that you've done calculus before and the way that we're going to use it, they're related, but they're going to feel different, okay? So I like to use this analogy. Math classes are just teaching you about tools, okay? So in a math class, they'll say, here is a hammer, here is a straight edge, here is a screwdriver, here is a wrench, and they'll be like, okay, here's a bunch of things you can do with a wrench, here's a bunch of nails, hammer them into wood, here's a bunch of screws, screw them in. Some of these screws are big, some of them are small, you know, stuff like that. Physics is like, now I would like you to build this house. Okay? So you've learned what all the tools are, you've learned what they do, but we're asking you to do something much more robust with them. You are not just hammering in nails anymore. You're wondering, if you hammer in this many nails on this board, will the house not collapse and kill you? Okay, so, well, I guess that gets into engineering. But it's all related, but we're applying what we learned now. Okay? So, we're going to start with some definitions. Usually we call position X, Y, or Z, but because position can be X, Y, or Z, when we want to just generally talk about position, it's usually written as R or S because everything is stupid. But let's start with S. Now remember, S can be X, Y, Z. It can also be R and theta. It's very general, okay? Because it depends on our coordinate system. And we will spend some time talking about coordinate systems. Then we have velocity, okay? And velocity is essentially speed, but it's a vector, so it's speed with a direction. All right? So if I say you're going 60 miles per hour, is that speed or velocity? Speed. If I say you're going 60 miles per hour due west, velocity. Okay? So you have to have speed and direction. We also have acceleration. Now, people get velocity and acceleration mixed up all the time. Okay? In your car, if your speedometer is not changing and you're going in a straight line, what's your acceleration? Zero. Okay? Velocity must change, but remember, velocity is made up of both speed and direction. So if you're going 60 miles per hour, and it just reads 60 miles per hour, but you're cranking the wheel to the left,
You got some acceleration.
you are accelerating. Even though your speed hasn't changed, what's changing? Direction, unless your steering wheel's broken, okay? So you've changed direction, and now you're experiencing acceleration. And you know what acceleration feels like, okay? If you're in a car going at a constant speed, if you're just going even 20 miles per hour, okay, do you feel like you're moving? If you blacked out all the windows, which you shouldn't do while driving, but if you blacked out all the windows, would you know you were moving? No, if you put a cup of coffee on your dashboard, let's say this is not a San Diego road, but somewhere where they paved the roads well, and they're not very bumpy, okay, and you have a nice, smooth car, you got a brand new Tesla, you're driving in a straight line, you're going 20 miles per hour, but you're not speeding up, slowing down, or turning, that coffee cup's going to sit right there as if you were in your living room, okay? But if you hit the gas, or if you hit the brake, or if you turn a corner, then what happens?
Spill your coffee.
Your coffee is spilled, and hopefully it's cold brew, so otherwise you're going to have a lawsuit on your hands when you scald your legs. But, so, acceleration is what will spill your coffee, okay? It's a change in speed, it's a change in direction. Speed, right, that's just a change in position, okay? And when we say change, what we really mean is derivative. Okay, so we also have to worry about time. Here's the variables we're working with, okay? So when we have these variables, if you want to go from position to velocity, and we're not writing these as vectors yet, but you know they are, okay? When you're in 1D, it's kind of iffy if it's a vector or not. 2 and 3 dimensions, then you have to get real vectoring. But if you take the time derivative of position, right, a change in position with respect to time gives you velocity. Okay? If you want acceleration, then you take a time derivative of velocity, which is also, if you've taken 2 derivatives, now that is the second derivative of position. Okay? So if you want to go from position to velocity, take a derivative. If you want to go from velocity to acceleration, take a second derivative. Okay? If you want to go back the other way, what do you got to do? Integrate, okay? So you have to integrate to go the other way. Now then there's these special cases where things are 0, but they mean different things depending on which variable we're talking about. So at position 0, what does that mean? Yeah. So, okay. In problems, a lot of times we're told which position is 0. But let's say you're just standing here. Let's say I'm standing here and I walk over here. Which thing is 0? Well, we can,
Whatever you want.
Your starting point?
It's in reference to what you're looking for.
whatever you want it to be. Okay? So this can be 0. And then if I walk 2 meters that way, my new position is now 2 meters. Okay? Or let's say this is 0. Then I start at -1, and I walk past 0 to +1. Okay? Or let's say we call this 0, and I start at -2 and walk to 0. Okay? That is why we have coordinate systems. Coordinate systems give you a reference so you can measure things. But what was the same in all cases? The total distance I walked. Okay, so that, yeah, and that would be called the displacement. We'll talk about that in a minute. So there are some things that don't depend on coordinate systems, and there's a special word for that. It's called invariant. It's an invariant quantity. And that's because, look, if I walk from here to here, I can pick any coordinate system. It doesn't change what actually happened. Okay? So the distance I traveled can't change depending on my coordinate system. My start and end points can change because I can change what I set up as 0, but the total distance I traveled, the displacement, can't change. Okay? So physics is just building a way to make sure we can quantify things that are actually happening. Okay? If it doesn't match with what actually happened, it's not a good system. All right? Okay, so this just means the particle is at the origin. Position equals 0 means particles at the origin, which is the origin that you pick or you are told. So position equals 0 is not that big of a deal. Displacement equaling to 0 gives you a lot more information. Okay? Let's say that we have v equal to 0. When can your velocity be 0?
You're not
Yes. When you're not moving, yes. Currently, if this is my reference frame and it's not moving, right? My velocity is 0. I'm not moving. Any other thoughts?
You said when we're at rest, so when you're not changing your speed.
So you can have an instantaneous velocity of 0. So for instance, if I throw this thing up in the air, it starts with a big speed. What does it do as it goes up?
Slows down. Right?
Slows down. What does it do up here?
Stops.
Stops, and then it turns around. So velocity at this point, 0. Does that mean the pen is not moving? No. Yes, changing directions. You always have a velocity of 0 right at the moment that you change directions. Okay? Because it's impossible to be running full speed this way and then immediately be running full speed that way. If you're changing directions, you have to slow all the way down to 0 and then speed back up. Okay? All right. So you can be momentarily at rest, instantaneously at rest. You can be stationary, or you can be changing directions. Okay? What does acceleration equals 0 mean?
Constant velocity.
Can mean constant velocity, and that velocity that could also mean 0 velocity, but it has to be a constant 0. Yes?
All forces acting on it are equal.
Yes, it also means all forces acting on it are equal. We haven't talked about force yet, so you're getting ahead of the game. But that's fine. Basically, it means the velocity is constant. So if you're going 2 miles per hour, or 10 miles per hour, or 60 miles per hour, but you're not changing direction, you're not speeding up, you're not slowing down. And obviously, if you're standing still. But the point is, acceleration equals 0 does not mean you're not moving, necessarily. Okay, sometimes it means you're not moving, but it doesn't always mean you're not moving. All right, here's another thing. Maximum and minimum. Okay, so like if I throw this up into the air and I want the maximum position. In calculus, how do you find maximums and minimums? Take a derivative, set it equal to 0, solve for the variable you're looking for. Okay, so that is totally true in physics too, and that's what it's for. So if you want to find the maximum position, take the derivative of position with respect to time, set it equal to 0, solve it for time, plug it back in to solve for s. Okay, same with velocity, same process, just v instead of s. Okay? All right. So this is my sort of summary of all the stuff. So now we're done with this chapter. No, we're going to go through this in a little bit more detail, but this is pretty much everything you need to know for kinematics generally. Okay? So, just what does kinematics mean?
Things moving around?
Basically. What language is kinematics? Math. I think it's Greek, right? So it's saying motion. Okay? So it's just Greek for motion. I don't speak Greek, but I assume that's correct. Anybody speak Greek? No? That sucks. It makes life easier in physics. It's a lot of stuff in Greek. So there's 3 basic types of motion. Okay? We have translational motion. That's basically just moving in a straight line. Okay? We have rotational motion, which is stuff that spins or pivots around a point. Okay? And then we have vibrational motion, and that's just stuff that jiggles. Okay? So those are our 3 basic types. We're mostly going to start by talking about translational motion. Then later in this class, when we start talking about torque and moment of inertia, things like that, that will be rotational motion. And we don't talk too much about vibration, but we will talk a little bit about it when we get into simple harmonic motion, which is stuff that oscillates. Okay? So we're going to start with translational motion. So this is a thing that's happening in a real life. Okay, or it could, assuming it snowed here. But look, we have a dog pulling a baby on a sled. They're moving in a straight line. This is just a video of it, so it's a 2-dimensional representation of a 3-dimensional thing that's happening. But if we want to pick a variable, if they're moving on a straight line, what axis would we call that?
X.
Yeah, you call it X. Okay, you can call it Y or Z. That's just notation. But the best thing to call it is X because we usually call horizontal things X. Okay? So, we want to represent these things in a simple model. So let's start with the dog, okay? So let's say we wanted to sort of recreate this. So we're just going to say, okay, this dog is moving from here to here. Okay? Now, do you want to draw a dog every time you have to figure out how far a dog's running in a problem? No. So we have something called the particle model, which basically says make everything a dot. Okay? So, and when we make it a dot, we make it an infinitely small dot, but those are hard to draw too, so we just pretend it's really small, and it doesn't have any mass, and it doesn't have any size. It's just easy, and it's the simplest possible thing. Okay, we can add detail back to the dog if we decide that we need it. So here's our dog. Now it's a dot. Okay. Ironically, this dog's name is Spot. Now the dot moves. Cool. Okay? Now we have to think about things like where does the dog start at 0? Does the dog end at 0? What do we put our coordinate system? We have to define these other things, okay? So we're going to start by first turning all things with shape and size into dots. All right?